Hi everyone, and welcome to the video on section 7.4. In this video we're going to be going over some specific kind of general families of differential equations and their solutions, all dealing with exponential growth and decay. So we're going to start off with this first formula, which we've seen something very similar to this before. This is a very common differential equation, and it's connected to exponential growth. So here it says the change in population, P is usually population, with respect to time, is proportional to the size of your population. Okay, so in your written homework, you saw something similar to this, right? In the written homework, it wasn't quite proportional to that. So this is the written homework, right? You had K, P, and then 1 minus P over M. So close, similar, but same idea. You're proportional to something about the population. Okay, this one's a little bit simpler than this one, right? And so, this is very common. It shows up all the time. Compounding interest, it shows up in the way bacteria grows, just all over the place. So we're going to talk a little bit about the solution to this and then apply that solution to a few different scenarios. Then I'll kind of show you how that works. All right, so often this is rewritten in terms of y to be more general in t. So instead of population, just a general function y. And we can solve this, right? So we know how to do this. dy dt equals k times y. All right, this is separation. We could separate all the y's on the left, all the t's, which there's only the dt on the right. And I like keeping the k, the constant, on the right, although you don't have to. And then remember, we integrate. So integrate dy d over y equals integral k dt. Okay, this is going to be the natural log of y equals, and then over here integrating, this is going to be kt plus c. Okay, so all right, hopefully that's not too bad. Now y is always positive because we're usually thinking of this as like population. So for these types of scenarios, we're going to keep y positive so that we don't need the absolute value here on natural log. And then we're going to actually solve for y here. So I'm going to do e to the natural log y equals e to the kt plus c. That's going to give me y equals e to the kt plus c. And then we end up doing a little bit of extra algebra here to make this look nicer. And so, because this is kind of weird up here. So this is equal to e to the kt times e to the c. Remember, our exponent rule says you multiply two of these, you add the exponents. So I'm just kind of doing that rule in reverse. And then what often happens is this constant here. Because remember, c is just an arbitrary constant, so e to the c is just a number. This is often melded into just one symbol, which just so happens to be the initial value of whatever you're talking about. If you want to hold on to population as we're going through here, that's fine. But it could be the initial amount of money you put in the bank. It's just the initial amount. And so altogether you get this formula right here. And so this is the formula we're going to be working off of for the first few exercises in this example right here. This is our big formula. Boom, boom. Okay, and so below this, we're not going to go through this, but you can kind of read through. It's just talking about like what each piece is, but I'll just do that up here. So let me zoom into this a little bit, and we'll talk about each piece. So y is just the quantity that is growing or decaying, population of something, money in account, whatever it is. This y0, again, it's going to be your initial. You could see that up here too, right? Because it's what happens at 0. And usually, this input value is time, so t equals 0. And then the other piece here is this k. This is called the constant of proportionality. Okay, but more specifically, this is going to tell you, am I growing, am I decaying, and how. All right, And it just so happens that if this is positive, I'm growing. If this is negative, I'm decaying. And if you're having trouble kind of figuring out, like, well, why would that happen? Just strip away some of this and do this. E to the kx. Now make k positive. What's the picture look like? Oh, it's that. E to the kx. Now make k negative. So, like, just pick something simple. -1. E to the negative x. Oh, that's that. Boom. That's it. That's what's happening there. That's it. It's just, if you have e to the positive power, it goes up. E to the negative power, it decays down. So that's all that they're doing there. And so we can use this formula. We can take some different pieces of information, we can plug it into the formula, use it, and kind of vice versa. And so that's what the first few problems are going to be, is we've got scenarios where we're going to apply this formula. So we're going to want to remember it. So let's just jump into those. Okay, so this example says we've got the bacteria E. coli, and when you have cells, you're often talking about how they grow. So in this case, we say a cell of this bacteria will divide into 2 cells every 20 minutes. So 1 cell becomes 2 cells every 20 minutes. Okay. So you gotta just think about what it means. What's happening? Doubling. This is doubling. Right? And if you're having trouble figuring out, like, wait, why is that doubling? Just take 2 simple scenarios. I start with 2 cells. What happens after 20 minutes? Well, they each become 2 more. And so if this was my start, where I had 2, after one kind of cycle of this, I now have 4. Doubled. 1 to 2. Doubled. This, if you do it out again, 2, 2, 2, 2, that will have doubled to 16. So, or sorry, 8. Can't even double. So this next one would be 8, and then so on. So this is just, I've doubled. So you see something like this, it's called doubling. Okay, that's going to be important in a second. So A says, find the relative growth rate. So what do we mean by that? Well, we mean our formula is going to look like this. Y equals your initial amount of bacteria, e to the kt. Right? This doubling fits here. Okay. So what do we know? We know it doubles every 20 minutes. So then 1 cell will become 2 cells after 20 minutes. So our formula needs to do that. Our formula needs to take in 1 cell, produce 2 cells after 20 minutes. Now, be a little careful. T is in hours. Hours. So then when we put 20 minutes, right, 20 minutes is actually 1/3 of an hour. So just be a little bit careful there, okay? But then this isn't too bad. We can solve this. So that would be 2 equals e to the 1/3 k. Okay, let's natural log both sides. ln e to the 1/3 k. Boom, goodbye. So this is going to end up being ln 2 equals 1/3 k. Move that over. 3 ln 2 equals k. And so k is going to be, let's take it and put it in our calculator. So the k is going to be 2.079. About. So that's rounded. Okay, so we've got our value for k. It's going to be our relative growth rate. Okay, so B is find an expression for the number of cells after t hours. So that's going to be y equals, this is B. Well, what did we start with? This problem said 60 cells, E, and then we've got 2.079 t. Because that was our k. Boom. So this was A. Okay. Find the number of cells after 8 hours. Well, that's not too bad. 60 e to the 2.079, 8 hours. So we can plug that into our calculator. 60 times e to the 2.079 times 8. Okay, that's going to be about 1,003,083,469 cells. Wowza. So that's a lot of cells, right? So hundreds, thousands, millions. over a billion cells. A lot of E. coli. About to get real sick. Find the rate of growth after 8 hours. Okay. So if we're trying to think about like, okay, you know, what happens here? Well, how is y prime growing? Well, any function, how it grows, take the derivative. So this is y, 2.079t, take the derivative. Okay, y prime equals, so that's going to be 60 times 2.079 e to the 2.079, and then t, we'll just leave it as t for a second, but we want to know what this is at 8 hours. So then we plug this in, but an 8 now goes up here for t, so I'll just rewrite it, times 2.079 e to the 2.079 times 8, and then that's going to be our growth rate at that time 8. So let's multiply this out, 2.079, and that's going to be about 2085410,532. Okay, cells per hour. So over 2 billion cells per hour is the growth rate at that point. So fast, okay? Fast. We're going quick at that point. It's really ramping up. It's exponential, so of course it is. But we're really, really kicking it into high gear here. So let me box these. So this is trying to give you a feel for this idea of exponential growth. It's very fast, right? It starts off like, oh, 1 to 2, 2 to 4, ha ha ha, this isn't anything, and then boom, you're at 1 billion. When will the population reach 20,000 cells? So let's give ourselves a little bit of room here. Okay, we want to know 20,000 cells. Well, just plug into our formula. That's 20,000 equals 60 e to the 2.079 t. So this is just algebra. Just get the t by itself, right? So this is going to be 20,000 over 60 equals e to the 2.079 t, right? You're going to log both sides. So we're going to put the 20,000 over 60 in, 20,000 over 60. So that's going to be log of 333.33 bar equals, the log on this side will cancel, 2.079t. So then we can divide over, take this, divide over, we're going to end up getting 2.79 about hours. So it's going to take a little under 3 hours to go from 60 bacteria in your gut to 20,000. And we saw, you know, it doesn't take too many more hours to get into the billions. Okay, so we've got an example, we used the formula, we got our growth rate, we used that to get a formula, like fill the formula out, and figure out a whole bunch of stuff. Okay, so next example. Strontium 90 has a half-life of 28 days. So this, again, is just another specific example of using this formula. Okay, so we're just back in this formula. Now, half-life means that after 28 days, whatever amount you had to start, and to stress this, it does not matter what amount you had. You could have had 1 milligram to start or 500 pounds to start. It will half in 28 days, okay? So we got to use this. So let's start with A. A sample has a mass of 50 milligrams initially. Find a formula for the mass remaining after t days. So what do we need, right? We need K and we need the initial. Well, we got the initial. That's pretty easy. So let's just write that down. Let's write down what we know so far. Y, the amount of strontium 90 remaining after t days, will be equal to 50 to start, e to the kt, where now t is in days. Okay, what do we know? We know that after 28 days, there's half remaining. So there should be 25 milligrams remaining after 28 days. So stop and make sure that that is okay. I half my amount, that's these two, in 28 days. That's enough for me to figure out what's going on here. So move it over, 1/2 equals e to the k times 28. And I want you to focus on this because this is something that might be useful in the future. Look, it didn't matter what numbers I started with. I could have made this 1,000,000 milligrams. I'm going to divide and end up with half equals this. So just kind of think about that a little bit. Then I'm going to log 28k, and then I'm going to divide. So altogether, I'm going to get that k is natural log of 1/2 over 28. Now, let's just plug that in the calculator so we can get an approximate answer, right? But one thing you should be noticing right away is this is going to be a negative number because log of a number less than 1. But that's good because it's decreasing, right? We said that we were losing it. Half-life, it's going down. So that's a good thing. This is negative 0.0248. Just doing some rounding. So okay, so all right, that's perfect. That's what goes in for k then, is this number. All right, so B says find the mass remaining after 40 days. So okay, B, y equals, I start with 50, e to the, and we'll just use this rounded number, and then after 40 days. So just plug into your calculator. All right, so let's do it. 50e to the negative 0.0248 times 40. That gives me approximately 18.54 milligrams. So after 40 days, this is how much is left. So let me just stop here and add another piece to this. Another interesting, thing you could use this for is, let's say that you were a medical professional giving a drug to someone. Well, the drug enters their system, and then their body starts to absorb it, and then the level of that drug in their system will increase, right? And then at some point, it'll start to decrease. And so this would be a very useful way to think about how much drug needs to be in their system to have the effect you want, right? And you could, depending on the person, because it's more complicated than just this is true for all people, right? But depending on the person, you could model what the amount of drug in their system would look like, and then you could get an idea of when it would go below or above a threshold you might need. And so this is another way that you could think of why this is useful, measuring concentrations of something in chemistry or in medicine, just as an aside. So, okay, hopefully not too bad. How long does it take to decay to 2? Well, this is just going backwards. I want 2 milligrams at the end. Get me time. So we can do that. Not too bad. Times t, we don't know it. So we just solve for it. So just go solving, right? 2 over 50 equals e to this negative kt. And then you're going to log both sides, right? So we'll get log 2 over 50. You want this to be negative so that they cancel later. Log the right side, the e goes away, 0.248t, and then divide. So your answer with slightly more precision is this, but that's not very helpful, so we're going to plug this into the calculator to get an idea. So it's going to be natural log of 2 over 50 divided by negative 0.0248. That gives me t equals 129.79. And again, approximate. All right. So going back up here, it takes almost 130 days for strontium 90 to go from 50 milligrams down to 2 milligrams. There you go. Okay. D says sketch the graph of the mass function. We can do that. We can do a pretty quick one here. So let me give us some more room. So d, okay. So what is this going to look like? Well, where do we start? We start at 50. Here we go. And then this is exponential decrease. So then we know we can use a couple of these numbers if we want to. It takes 130 days to get down to 2. What else did we do? It took 28 days to get down to 50. It takes 40 days to get down to 18.54. So you can try to fit this a little bit better, but you just need the basic, right? You just need the basic shape of an exponential. Decrease, decrease, decrease. But then the decrease is faster at first, but then it's starting to slow down as it approaches 0. So here's an extra little tidbit for you to think about. And this is a small strike against, using these formulas in the real world. So this is like a little extra tidbit. At what time is the concentration equal to 0 milligrams? So it's something for you to kind of think about off to the side, right? If this formula really is telling me what, or the mass, so I should use mass there. If this formula is telling me the mass of strontium 90 that I have, right, starting with my 50 milligrams, when am I going to hit 0? When is it going to all decay into nothingness? So try that. Try thinking about that. Try seeing if you can figure that out. As I let time go bigger and bigger and bigger and bigger, what happens to this y? So an interesting little kind of side tidbit. Okay, so that's our more basic, not that that's basic, but our slightly simpler in terms of the formula setup, exponential growth and decay. Now the other kind of big one in this section is Newton's law. So Newton's law is a little bit different. It's not quite just proportional to some value. There's a little bit extra here. So read through this. Newton's law is giving us a way to try to find the temperature of an object at some time, t, where that temperature of that object is different than its surroundings. So what's the classic? You've got a hot cup of coffee or an ice cube or something like that, where the hot cup of coffee, you leave it out, it's going to cool down, cool down, cool down until it gets to the room temperature. So that can be modeled by Newton's law of cooling, and basically the whole idea of it is that how is the temperature of the coffee going to change? It's proportional to the difference between the temperature that it currently is at and the surrounding. So just kind of stop and think about that for a second, right? You want to cool something off. Well, you can put it in the fridge or the freezer. Why would you put it in the freezer? You want it to cool down really, a lot quicker. Why would you put it in the fridge? Oh, it's okay to cool down a little bit slower. Why does that happen? Well, that's what the equation says. The difference between your hot thing and the freezer is going to be larger right here. A larger number makes this derivative bigger, which means the change is bigger. So that's what this equation is trying to tell you. Okay? So we can get a little fancy here and do a little substitution to solve this equation, okay? Which isn't actually too bad to do. So I'm not gonna. It's not something I'm gonna make you do to do this. But this is an interesting idea that this is almost kind of like a U sub that we're doing here, and you could actually do that, right? So just think about it this way. If I wanted to solve this, move all the big T's on one side. This would be dt over t minus ts equals k dt. And then I would be what? Integrating. And then how would I solve this left integral? Well, I would do a u sub. U equals t minus ts. Now, because y is our general variable for these types of problems, they do a y sub, not a u sub. But it's the same idea. that you're going to end up, very, very similar formula. So in any case, either we just kind of go through and solve this problem without even thinking about any of this and use a u-sub here, or if we want to use this little tricky change of variable, it's kind of like doing a u-sub before you even integrate it here, we're going to get to the same place. So we're going to get to, if you go this way, y equals, and because we know how to solve this, right? So this would be y0, right? But we have to be a little careful when we're applying this. So y0, I'll talk about that in a second, e to the k little t. But if we're going this way, y is actually big T minus the surrounding temperature equals, and then y0, well, what's y0? That's T0, so the initial temperature of your object here. So we just got to be a little bit careful when we're doing this. Either way you do this out is fine. But this is what the formula ends up looking like. And so you can then move things over if you want. Your initial temperature of your object minus the surrounding, e to the kt, plus the temperature of the surrounding. Okay? So that's your formula. It's a little more complicated, but it's not too bad for Newton's law. So let's see what it wants us to do. We've got a murder investigation. The temperature of the corpse was 32.5 degrees Celsius at 1:30 and 30.3 degrees Celsius an hour later. Normal body temperature is 37 degrees, and the surrounding was 20. When did the murder take place? Okay. So we've got a lot of options on how we can actually do this, right? But let's just write out some notation. We're going to let big T represent the temperature of the body. Okay. Now, here's the thing. We have to talk about what little t is going to be. Like, how, what's our frame of reference for little t? So we've got, some times here, 1:30 p.m. But we could fix t equals 0 anywhere we want, really. It's kind of up to you where you want to put t equals 0, as long as the rest of the times you're going to deal with, you understand the number you get out, how that connects. One way to do this is to make t equals 0, 1:30 p.m. I'm given a specific time. Let's just nail that down as t equals 0, and any t we solve for later, we're going to have to just think about what that means compared to this 1:30 p.m. Okay. You can do other things though. You could do something like, here's your options. You could say, let's let t equals 0 be the murder time. That's trickier because you don't actually know when that is, so it's harder to write 1:30 in regard to that, right? So that's pretty tricky. You could let t equals 0 be, just noon if you wanted, which would mean 1:30 would be at what? That would be at t equals 1.5 hours, because that's 1.5 hours after noon. So you got a lot of options here, but I think it's simpler to make the known number just 0. Make that t equals 0, okay? So then what do we know? We know that at t equals 0, this was the temperature. We know normal body temperature is 37. Okay, we know the surrounding temperature, Ts, is 20 degrees. Okay, so we have our formula, right? We already wrote it down up here. So let's write it down here. T equals the initial temperature minus the temperature of the surroundings, e to the kt, plus the temperature of the surrounding. So we got to be a little careful here. TO is the temperature at time 0, but that's 1:30 p.m., right? So let's go back here. That was 32.5 degrees. Okay, so 32.5 minus the surrounding is 20 degrees, e to the kt plus 20. Okay, so we're cooking a little bit here. We got some stuff going. So this is 12.5 e to the k t plus 20. Okay, so there you go. That's going to be our formula. So, all right, that's not too bad to start. The problem right now, though, is we don't actually know what k is, right? So we don't have k, but we have another piece of information that's going to help us get there. 1 hour later, we know we get this temperature. So we're going to bring in that 30.3 degrees Celsius. It's going to now come into here because that's the temperature after 1 hour, right? T is time after 1:30. We know 1 hour after that, we got to this temperature. So we're going to solve. That's going to be 10.3 equals 12.5 e to the k. Divide over. Log both sides. 10.3 over 12.5 is k. Okay, so then we could plug that in our calculator. See what we get. So that'd be natural log of 10.3 divided by 12.5. That's going to give us k is about negative 0.194. Okay, so we know k now. So we could plug that into our formula. So our formula now becomes the temperature of the body at some number of hours after 1:30 is 12.5 e to this k t plus 20. Okay, awesome. We have our temperature. So here's the thing. Let's go back. What did we want to know? We wanted to know when the person died. Well, when they died, they had 37 degree temperature body. So this formula, I know this is a little bit weird. We're going to use this formula to work backwards in time to get back up to 37 degrees. We want to know when this formula tells us we were at 37 degrees. So let's solve. Okay, you're going to move the 20 over, divide. So this will give us 17 over 12.5 is e to this kt. Log both sides. So that'll be log of 17 over 12.5. Right, that'll cancel with the e and then we divide. I'm doing this a little quicker because we've done this a few times now. That's going to be t. So let's plug that in. Log of 17 divided by 12.5 divided by negative 0.194. And that's going to give me about negative 1.58 hours. Okay, and so at this point you might be like, well, Mr. B, come on, you always said no negative time. You got to be thinking about that. In this case, negative time is actually okay, right? Because the whole point of this was we know things that have happened in the future to this temperature, and we want to go backwards to figure out what's going on in the past, a time in the past. So negative on here is good because it's telling us to go back before 1:30 p.m. How much before? Well, a little over 1.5 hours earlier. So what we need to do then is we need to go, this is going to say, go 1.58 hours before our t equals 0, which was 1:30 p.m. Okay? So, we can do a little, 1.58 is pretty close to 1.5 hours. So if you were trying to, just kind of be a little quick with this, you might say, okay, this is basically 1.5 hours, which would get me to about noon. So you could say that this is approximately noon. If you wanted to be a little bit more precise, you could convert 1.58 hours into just minutes, right? So you gotta be a little careful there, but we can just do that quickly to the side, right? So 0.58 hours, right, times, there's 1 hour to 60 minutes, okay? And so let's do that. Oh, I wrote 6 minutes. That's not true. 60 minutes. 0.58 times 60. So it's 34.8 minutes. So then to be more precise, right, we want to take 1:30 p.m., go back an hour and 34.8 minutes. So if we do that, we'd go back an hour, that's 12:30. Go back 30 minutes, that's 12. And then go back another 4.8 minutes, so about 5 minutes. So really this happened around 11:55 a.m. is when the murder happened. And there you go. So a little bit of a crazy problem. I think the toughest thing is getting yourself oriented with when t equals 0 should be. And there is, again, a little choice there. But what's easiest usually is to make t equals 0 one of these numbers that you're given, a time you're actually nailed down. So that's that 1:30. And then from there, you can, any time you find just has to be in reference to 1:30. We found negative 1.58, so that was take 1:30 and go backwards. This said an hour later, so then take 1:30 as your 0 and go 1 hour. T equals 1. So I think that's the trickiest part of this. But that's it. There you go. That's an example of Newton's law. Pretty cool idea. Hopefully not too terrible to use these equations. Of course, if you have any questions, you have to just let me know, and I'll see you in the next video.